organic chemistry, most of the mechanisms, they are similar in the sense that if we have a electrophilic substitution, all of the electrophilic substitution, at least most, they would follow the same mechanism. And the mechanism, the most basic thing to remember, is nucleophile to electrophile. So that's how we start the analysis of mechanism. You always need to find the nucleophile, then the electrophile. Benzene, even though it's has less electron density than an alkene, it's unable to polarize and all of this, it's still a region of electron density. So it will react with an electrophile, which I'm going to write as E+, because it's the general electrophile, which means that it will always attack that electrophile. The first curly arrow, it starts not directly from the middle of the ring. Very important, it starts from that line. I would suggest you to always remember one way to draw it and repeat it many times, just as a habit to know where that arrow starts from. The consequence of this would be, well, an intermediate, a positive intermediate. So these delocalized electrons, they're now not there anymore, but the positive charge will also be delocalized along all of the carbons, leaving just that carbon with the electrophile attached there. Right? So it's important to have this like horseshoe, something like that it's called, the shape that covers all of the carbons. So that we have to be quite picky with where the positive charge is distributed, because just like the double bond is delocalized across all of the 6 carbons, so is the positive charge, apart from, of course, the carbon where the electrophile is now added. The aromatic is extremely stable, so it will always reform the aromatic group. That's why in the next step, we write the hydrogen. Of course, remembering that hydrogen is present actually on each of the carbons, because we know that benzene C6H6, so it has 6 hydrogens. The electrons will go back to the ring to form our substituted benzene and H+ as the side product. It's really important to know the general mechanism, because when we see the generation of the electrophile, well, the mechanism will always be the same. And this is called electrophilic substitution, because an electrophile has substituted an hydrogen. The tricky thing to remember in this mechanism, apart from, well, a little bit of logic, knowing that where the arrows start, the positive intermediate, also the fact that the aromatic always reforms, it's how the electrophile is generated, because benzene is not reactive enough to polarize a molecule, so it doesn't form this delta positive like alkenes. So we need to generate the electrophile. There are, I would say, 3 main reactions. First one, it's anything that's involved with halogens. Well, let's go with the first one, halogenation. The halogenation, we could have the addition of bromine or chlorine. With chlorine, we'll see it after, because it's a common catalyst for the other reactions. But the bromine would react with a catalyst. This catalyst is ion bromide to form the electrophile, and the intermediate ion bromide with a negative charge, and leaving behind a much stronger electrophile because it has a formal positive charge. Notice that there are just the 3 bonds, so it's an electron deficient transition metal or transition metal complex, and that's why it can form actually a dative covalent bond. So we can see that in this there is an heterolytic bond fission, because the electrons from the bromine, they would actually go completely, they will bond completely. Can I rotate it? Let's do it like that, just to make a sense of it, to the transition metal catalyst to form these complex with a negative charge, and this leaves behind, of course, bromine with 1 less electron than before, because 1 is now in this complex, so it has a positive charge. So that's how a catalyst, how this catalyst formed. In fact, at the end, when we look at this mechanism where the aromatic ring has to be regenerated, the bromine minus that comes from this complex FeBr3, it's what takes that hydrogen. And this helps us to understand also what's the side product of this reaction. Because to reform the catalyst, and this is a common exam question where you are asked, okay, show the equation to reform the catalyst. Well, this FeBr3 Vr4 minus will react with that H plus to form the side product of the reaction, which is HBr, and reforms the catalyst. That's why, of course, in the overall equation of benzene, so C6H6 with bromine, the catalyst, well, we don't really need to add it because we know that it's reformed at the end of the reaction. But it's useful to understand how that works, because with the other, well, with the chlorine, it would be really similar. But understanding the mechanism helps understanding also what are the side products. So we need that when we have to write the overall equation. So the other type of halogenation is with chlorine. But we have not only halogenation with chlorine, but also two others that have a common catalyst: alkylation and acylation. So with halogenation would be chlorine. With alkylation would be adding an alkyl group, and an alkyl group is just a carbon chain. So let's give an example of CH3, and it would be CH3Cl. And then acylation, it's the carbon double bond. So this would be an acyl chloride. So let's keep it simple: carbon double bonds, and then chlorine. I'll do the display formula just to make it a bit more sense. All of those use the same catalyst, which is aluminum chloride. And it works in exactly the same way, because notice that it's also electron deficient. So it would form chlorine plus as an electrophile. Here we leave the carbon with the positive charge, because the chlorine is taken away in all these cases to form the complex aluminum chloride with now a negative charge. So in all of these three reactions. So, but if it takes away the chlorine, then what is left behind is the carbon with the positive charge. And here as well, we would have this hydrogen carbon double bond with a positive charge. That's how the carbon can become a much stronger electrophile, because the dipole that the chlorine causes, it's not enough for the benzene to react. So halogenation, alkylation, and acylation uses the same catalyst, this aluminum chloride. There is one more to look that could be a bit more complex to understand, but we link it to the acid-base topic, so it's always really, really useful to analyze it a bit more, which is the nitration. And for the nitration, we use HNO3, so nitric acid, and sulfuric acid, H2SO4. Because we have two acids react together, well, one will react as an acid and the other one react as a base. In fact, this is what happens. So let's say that I tell you that the nitric acid is a weaker acid, which means that it would react as a base. While the sulfuric acid, it's not only a catalyst, but also an acid, because it will form H2NO3 plus, because it's gained a proton, leaving behind this HSO4 minus, which is the intermediate that then it will form again the catalyst. But this is not our electrophile, because this dissociates further to form water and nitrogen dioxide with the positive charge. So this is the electrophile that benzene reacts with. So C6H6 plus HNO3. It will form C6H5 NO2, and it would leave behind water. That's the other product, and then we have the acid here. So the reaction, we don't need to write it with these acid-base intermediate, we can just write it remembering that we form the NO2 plus water and the sulfuric acid, because again, it's a kind of neutralization reaction. So in this step where the hydrogen is randomly taken away. Well, it's not so random because it's the HSO4 minus that takes that hydrogen to reform, guess what? The catalyst, H2SO4. So the catalyst reforms at the end by taking away that hydrogen somehow. And that's why it's useful to see how it's reformed, but also how really it works in terms of charges. So mechanism is always the same. Formation of the catalyst, it's an important part to fully understand the reactivity, and that these reactions, they have to be I would just say memorized, because they can be completely understood, and this will make it easier to retain them.